first speaker for the day, Barbara Terhal. Barbara is a professor at TU Delft and part of QTech in the Netherlands. She's really one of the pioneers in quantum information, I'm sure as many of you know, and works on error correction. A reminder that the Slack channel for questions is session 5, talk 1, Terhal. So please post your questions there, and we'll be taking questions at the end. We've got at least 10 minutes for questions at the end of Barbara's talk. And yeah, so it's a great pleasure to introduce Barbara, who's talking about phase estimation and stochastic Hamiltonians. Thank you, Barbara.
Yes, thanks, Steve. Okay, so now it's up to me to give this very virtual talk. I'm going to share my screen. Let's see. Enter some things. Wait 1 moment. Okay, let me just get everything up here. Yeah. Yeah, so I'm going to talk about something that is a little bit work in progress. And so maybe I'll get some feedback from you that's useful. And I know a lot of people work on variational approaches these days because we have NISQ machines on which we cannot run very deep circuits. And this seems like a very good approach. But of course, we also know that quantum phase estimation is the real workhorse of sort of, you know, purebred algorithms. And I did some work on trying to sort of cut some corners on phase estimation, you know, do some of the work classically. And then we also ask, and that is sort of some part of my talk, if you have stochastic Hamiltonians, so Hamiltonians which don't have a sign problem, is phase estimation useful at all? And this is also a topic that people have thought about already a bit. And I'm not sure that we have a definitive answer, but I'll just give you some of the things that we're researching. And then at the bottom of the slide here, you show end spectral quantum tomography, because some of what we did for phase estimation was actually very useful directly for some spectral tomography method that we invented that I'll also mention in my talk. Okay, so there we go. Okay, so I'm gonna go to the next slide. And where is it? Oh yes, here. It's a bit slow. Okay, yeah. Okay, so yeah, so one of the things, a very early paper by Abrams and Lloyd, Lloyd now sort of the Darth Vader of quantum computing, in PRL 9090 was the idea that you could do phase estimation to estimate eigenvalues and maybe ground state energy of a Hamiltonian. So let's sort of review the setup, because you're going to see some parameters that I'll come back to later. So first we have to start with some input state. Now ideally we want it to be some eigenstate of the Hamiltonian, but you know, maybe that's the exact state that we want to prepare, so we can't do that. We start with some state that is easy to prepare. So that's what I call with easy. It's some superposition of eigenstates. And I want to be working in a setting where the number of eigenvalues in this state, so the number of states for which this quantity is non-zero, is small. That number we call n. And why is it small? Because in general it's exponentially large, so then, you know, I can't determine all these eigenvalues. And the goal is a little bit, I want to not just determine one eigenvalue, I want to, you know, learn the full spectral content in this state. And the other thing we do, if we have some many-body Hamiltonian, we kind of have to rescale it such that all the eigenvalues fit in this interval 0 to pi, at least for the, you know, the eigenstates that are in S. And that defines a unitary U. And really the cost of phase estimation is measured by how often we have to apply U or controlled U. And that's what we want to minimize, because implementing U is painful. It's painful because trauterization is painful, and a lot of people are working on trying to, you know, be more efficient about trauterization or qubitization. But of course, we know that if I implant something like U to the K, then I cannot get around generically by having that scale with less than K. It will grow with K generically, except if I, you know, U is what I use in my factoring algorithm, then it actually is efficient. Okay, but for generic Hamiltonians, there's no shortcut in this. Okay, so we want to determine these eigenvalues. And now the proposal to cut corners, and this is, there are actually so many papers on phase estimation, way too many. I wish there people would write a better Wikipedia entry on all that's known, because I feel like some things get redone every so often. But anyhow, so I want to cut some corners. And first of all, I want to cut corners in a way that I don't want to prepare an eigenstate. I don't want to go from this state to one of these eigenstates in the superposition. I just want to determine these frequencies. So I got that state, and now I have a single extra ancilla, put it in a plus state, and I apply controlled U to the k, and then I measure that extra qubit in the plus minus basis. And then I can look at, what's the probability for plus in this? And it's not hard to show that this probability for plus equals this. And from that, you can make one observation, namely that if I just had a single eigenstate, say, phi 1 is in there and the rest, just one eigenstate, then if I were to repeat this experiment with k is 1, I could determine the eigenvalue. Why? Well, I just repeat this. I prepare the eigenstate, I apply controlled U, I measure the qubit, and I repeat that experiment. And on the basis of how often I find a plus or minus, I estimate the probability. Estimating the probability will give me an estimate for this cosine for k is 1. And okay, cosine is an even function, so I can't distinguish x from minus x, so I also have to do this with the sign, but you kind of get the idea. And but you can also observe that if you're only having k is 1, but you have more eigenvalues, then you get this signal. So this probability for plus or minus would just be this with the sum over n a n, and you can actually not learn all the mu n's from this. You can actually prove that you need to run this type of circuit for, say, k is 1, k is 2, up to some capital K. And what we like, of course, is this capital K is not too large. Now, there was this other circuit that I mentioned, which is the one that gives you very similar data, except that it's, if you look at the probability for this being plus or minus, it's related to the sinus, the sine function. Okay, so what we do, and I'll come back to how this relates to other forms of phase estimation briefly, perhaps. But we like this because we only have to run controlled U once, or controlled U to the k, and we'd like that k to be as low as possible, but we can't cut corners arbitrarily. We repeat this experiment, and every time we, this output state is just tossed in the waste bin, and we prepare a new state. So we're done after this cycle. Okay, and it uses one extra ancillus. Now, of course, if we have this probability and that probability, or if we have estimates of that, because we repeat the experiment some n sample times, this is n sample, is a number that's also relevant, then we can construct this kind of thing, right? The sine and the cosine, I can construct this. And this one I call the signal. And the idea now is to say, well, okay, I get this signal for k going from 1 to some capital K, from k1 to some capital K, and I'll get it with some sampling noise. And there will be n frequencies in this signal. So that's the task that I have to do classically, right? So so that's what I'm going to talk about now. Now, I have an extra slide. Maybe we can talk about this afterwards on why this form of phase estimation is no worse than other forms of phase estimation, because you may have seen phase estimation where k goes from to the 0, to the 1, to the 2, have exponential jumps. And my claim is that actually, I think with noise also, that, well, my claim is mathematically, this is no worse in order to estimate eigenvalues. Furthermore, it may be actually less sensitive to noise. Okay, but for now, we're just assuming we have these circuits and we implement them, repeat them. And you can see they're not requiring more qubits, but there are, of course, somewhat deep because of Trotter trouble. Okay, I put here analog phase estimation, but maybe I want to skip that. If anybody wants to know, we can ask at the end what I mean by that. Okay. No, next slide. Why is this slow? Okay, it's a bit slow. Yeah, okay, so now I want to actually refer. So this is what we did. So we asked, you get this signal, G of K, with some sampling error. And now the goal is to get the eigenvalue, mu n, and also to get the an. Yeah. Let me just see. This is some other stuff. Okay, sorry, I was just look at the chat window for a moment. Okay, then of course, if you know the an and the mu n, you can estimate this kind of quantity. And so what we did is we said this is a signal, and we'll use what we call what's called a matrix pencil technique to extract these and these mu n's. That's what we actually sort of reinvented this technique. At least we weren't aware that was called matrix pencil technique. And then there was another interesting paper, and I just want to point it out to you, by Somma, which did a very similar thing, but it's different, and I think actually in some sense it's better. What we'll see is that if there's no sampling noise on this G of K, meaning that you do this, you do this experiment so many times that there's really no error, you just get G of K exactly, then this matrix pencil technique is a very good technique to extract the eigenvalues, as long as the capital K, which is sort of this depth of the circuit, which is sort of like the time variable, how long do you run U, is it has to be large enough compared to the number of frequencies, which is sort of a natural type of constraint. So there's no sampling noise, the matrix pencil technique does quite well. There are results on how well it does in the presence of sampling that I'll discuss. But what you can actually say, well, for example, maybe there are eigenvalues in the spectrum that are really on top of each other. And then if you look at the results for this matrix pencil technique, what you see is that, oh, it's really hard to tell them apart because you need a lot of resolution if the eigenvalues are very close to each other. It's sort of an obvious thing. So you need your K to be very large, which is the depth of the thing you're sampling, and low sampling and so on. But of course, in some sense, we say, well, we actually don't care about, if two eigenvalues are right on top of each other, we just say, well, just call them the same thing. And actually what I want to estimate is the total probability for those eigenvalues. I'm kind of interested in the density of states in some sense in this input state. So what Somma did, which is sort of I don't want to sketch the idea, is that he says, well, let's just bin the eigenvalues in bins that are, say, 2 epsilon wide. So the eigenvalues, they sit in the interval 0 to pi. I bin them in this 2 epsilon win. And what I actually want to do is I just want to know the total probability for this bin. So there's these coefficients an, and I can define a vector a bin with coefficients n. And so this is the, I sum over all the eigenvalues in the ith bin to get, I sum over all the probabilities for the eigenvalues in the ith bin to get this coefficient. Yeah? So that's the kind of quantity I want to estimate. And the way he does it is to say, well, I can do this. So he also uses the signal G of K, with you get it, he assumes some with error epsilon. You have to ask how you get this error, how much samples, but let's ignore that for now. And you use K up to something that goes like 1 over epsilon. And then the idea is this, that you say, well, what I want is I just want to have I'm going to define ideally a function which takes the value 1 on bin J and 0 elsewhere. That's an indicator function. But I'm going to approximate this function by something that's a bit more smooth, which is shown here with a little bump function. And because it's more smooth, I can expand it in terms of Fourier coefficients. I kind of periodically repeat the functions. There are only a discrete number of Fourier components. And the nice thing is that I want these Fourier components only to range, for some limited amount, not too many, and that's set by this K. And so if you then look at a quantity like sum over n, an times the bump function in the jth bin, so this is an approximation for the total probability in this jth bin, then just, putting this equation into here gives you, and pulling out g of k gives you, that is the sum over k, g of k times these Fourier components, these Fourier coefficients. So you know the Fourier coefficients, you know the signal, and so you compute that. Yeah. So that's his way of doing this. And what I like about it is that it's because it says, well, you know, if eigenvalues are on top of each other, we don't need to distinguish them. This is a method for getting sort of the probability of all the, you know, in each bin using some Fourier analysis. Okay, so this is not. Oh, my slide forwarding is awkward. Sorry. Oh yeah. Okay, this is just a problem. Oh, it works. Yeah. Sorry, I'm just talking to myself. Okay. Now, so what's this matrix pencil technique? So some of you may have heard about this, some of you not. And in some sense, it's just sort of a generalized eigenvalue problem. A linear matrix pencil, meaning it's linear in the parameter lambda, is something like this. I have two matrices, G1 and G0. In our first example, there'd just be square matrices. And you want to determine the values lambda for which this determinant is 0. And so you clearly see if G0 is invertible, I could, you know, multiply G1 by G0 inverse, and then I just have an eigenvalue problem. So that's why it's a generalized eigenvalue problem. Okay, so what does that have to do with my signal and so on? So what I'm going to do is, first of all, we're going to write G of k as the sum over n frequencies, use the probabilities, and now the lambda n are these exponentials, oscillating exponentials, either the I, mu, n. But actually this method, one important thing to say perhaps, this method also works if the lambda n are complex and decaying. So they're a norm less than 1. Okay, so I got this information, and now I'm going to construct the matrices G1 and G0. And actually what I'm going to do, I'm going to construct a matrix Y, which is filled with these values G of k for G is 0 to some things. And the matrix G0 is the blue submatrix. So it's actually everything except the last column, and matrix G1 is the red submatrix. Okay, so just to make a little bit understand what's going on, we can, G of k is just a linear combination of these things. So I can write this matrix Y as a sum over n, a, n of this matrix. Yeah? So now what you can see is that if there's only one eigenvalue, so there's only one n for which this is non-zero, then the matrix G1 is just, you know, you get the second column by multiplying the first column with lambda, right? So you get actually the matrix G1 by multiplying the matrix G0 by lambda. Yeah, and then if you plug that in here, then you see that lambda is an eigenvalue. Yeah, and that's sort of the idea. So the point is that if I choose my k, let me see, k is depending on how much data I have. If I choose it large enough, namely 2n minus 2, you can actually argue that the GIs are square matrices and they're generically full rank. Now, if they're full rank, I can invert them. So I can construct something like what I call the time shift matrix. And the time shift matrix maps G0 to G1. Okay, so what I'm doing is I'm going to construct this time shift matrix, which I can do if I can do the inverse. In this case, I can do the inverse because the matrices are square, they're full rank. And then I'm just going to compute the eigenvalues of T. And then you actually see, well, what I was just doing, I was just solving this eigenvalue problem. Yeah. And the idea now is that the matrix pencil technique is more general in the sense that these matrices G1 and G2, G1 and G0, they're not necessarily square. So that will be the next slide. Now, once you have these guys, so once you have the lambda n, you can say, can I determine the an? And you can do that as follows. So you can see, we'll say, well, this looks actually kind of like an inner product between the vector A and the vector, some vector I construct with the lambdas. And I get these inner products for, you know, different values of k. K is 1, k is 2, up to capital K. And I can actually also write this as I have a vector A, and then this is, you know, for different k's, again, a vector G. And then this is a matrix. Well, this is now a vector, but I can make a matrix out of it for different k. That's a van der Monde matrix. And what I need to do, I need to invert this van der Monde matrix, right? Because it would be, you know, vector G and then van der Monde matrix on the vector K, vector A, and I want to determine vector A, so I just need to move this van der Monde matrix to the other side. And now the point is that if G of K has noise, so there's an error on it, and I apply this to van der Monde matrix, I have to deal with the condition number of the van der Monde matrix. So this is why noise is important. And this depends also on the lambdas, this condition number of the van der Monde matrix. Anyhow, so if there's no noise, then you can just argue you can get this. You have GK exactly, you can get the A exactly as well. Okay, so just let me mention what is known when there's noise. I don't want to spend too long about this. So let's say we have the signal now, and we have some error at eta K. Yeah? And I can take some norm of this error, some 2 norm, a measure of how much noise there is. And of course, I could bring down this noise by making n sampling larger and larger. And in this case, we need to actually take more redundancy. We need to take k larger than 2n minus 2. And we also, there's several techniques how to deal with noise. Actually, one thing we implemented, we map y to something we call y clean, in which we only keep the n largest singular values. So the thing is, like, we know there are n frequencies in the signal, so we need to end up with sort of n numbers. And so by keeping only the largest singular values, we throw away the sort of, you know, the singular values that are only there due to some noise. But then in general, you have non-square matrices. And then there is a result, and this is the result. Maybe there's one result, and there's actually another paper, but we didn't study this. So it's the result on saying that you can deal with noise, and what are the conditions on the spectrum in order to estimate every eigenvalue with high accuracy. And let me just paraphrase this noise, paraphrase this result. So what you need is that you say, okay, I got these mu n eigenvalues, you got n of them, and let delta be the minimum distance between them. You know, they wrap around, they're between 0 and 2 pi, so you have to, you know, also 0 should not be on top of, you know, 2 pi. So there's some wraparound there. So, but there should be some minimal gap. And then the k should be, you know, scaling at least inversely with this minimal gap. This is what is needed, which also, you know, also says that k has to be scaling with n because they're n eigenvalues. And if you have that, so if k is large enough, then one can handle the noise. And there is basically sort of a phase transition. If k is too little, or that's what he argues, if k is less than this, you can't handle the noise. You really are sort of wiped out by, in terms of, you know, you can't get any good accuracy. Well, you can get some accuracy, but you can't get it, you can't suppress it by sampling more and more. Okay, so you can construct both the mu and the a, and with some error that scales polynomially in eta and k, but you can, you know, if this norm can be made very small by getting more samples, you can suppress this epsilon. Now, one thing I want to mention that I had some initial discussions with people, that would be nice if we can show something for the signals that are not only oscillatory, but also decaying. And that's, and as far as I know, it has not been done. Question is how much, you know, can you prove such a thing, or is it worse? Okay, so now, let me see how I'm doing on time. I have to hurry up a bit. Okay, so now I just want to mention how we use this. So we use this for phase estimation. We also use it for this, what we call spectral quantum tomography. I know a lot of people like randomized benchmarking, or interleaved randomized benchmarking, but this is a technique where you say, it's not scalable. I'm trying to do this 2-qubit gate with high fidelity. and I want to know, how good is it? And I want to know this in a spam independent way. So I could do full gate tomography, but then it's spam dependent. So why don't I just try to determine the eigenvalues of the gate? Now, what are the eigenvalues of a gate? Well, you can take the polytransfer matrix. So let's take a gate, a qubit gate, a single qubit gate acting on a qubit. Polytransfer matrix defined like this, take the polys in, trace with the output poly. It's a 4x4 matrix. Here's, this is a one-dimensional block, and there's a three-dimensional block. So this TS works is a 3x3 matrix. And you can ask what the eigenvalues of this. Well, the eigenvalues you can prove are norm less than 1, and they're of this form. Yeah. Okay, so if I could determine, if I get some signal, and now the signal we're going to get is something like this. I prepare a poly, which you can do by preparing a qubit in different bases. Now there's some noisy channel, it's some spam thing, I don't know what it is. Then I apply my gates, k times, and then I do a measurement of another poly, or actually, sorry, it's the same poly. Yeah? And so nmesh and nprep are the spam. I don't know what they are. And, but for any nmesh and nprep, the signal is going to look like this. And these an actually will depend a bit on this spam stuff. But because the lab that are, decaying complex exponentials, they fit this scheme, so I could process the signal using my matrix pencil techniques. And we did this sort of for some gates, like on the IBM quantum computer and on a chip at Delft. And we made something which looked quite nice, a spectral footprint, which is something where if the gate, so we're plotting here the 3 eigenvalues of this matrix. If it's a unitary, they should all be norm 1. And so these should be these blue dots. And then what happens if the gate you do in real life, I'm not going to explain. So the eigenvalues are less in norm. So in this thing, there's the norm of the eigenvalue goes down if you go outwards. So here you see that the gate as this RH pi over 4 rotation on the IBM chip did worse than the chip in the Delft lab. Of course, we took these data to present. No, not really, but it just happens to do worse here. Okay, so this is informative. We also study leakage and non-covariancy. Okay, so in the last 5 to 10 minutes, I'd like to come back to kind of the title of my talk is phase estimation useful for stochastic Hamiltonians? And Sergey and I thought about this much in the past, and other people as well. So you could say there's a folklore belief if there's an efficient quantum algorithm to estimate the ground state energy of a stochastic Hamiltonian, meaning it has no sign problem, maybe then there's also a classical Monte Carlo algorithm. Maybe this is completely false, would be really great if somebody, I mean, there's some counterexamples for some techniques that you say, well, yeah. Oh, well, it's an open question. Let me say it this way. For frustration-free Hamiltonians, we know a little bit more. Okay, so that's a question about ground states. But now I'm not actually only interested in ground states. I was also interested in excited states, energy of excited states. And what I really want to ask is that let's assume that instead of having this complex oscillatory signal, I have a purely decaying signal. And again, U and N are the eigenvalues of a stochastic Hamiltonian. Now you can ask, well, great, but how do I get this signal? So I can tell you how you get that. And secondly, you can ask, okay, so now I want to extract again the mu n and the an in the presence of sampling noise compared with this. Now, one obvious comment of that is say, well, that's not going to work so well because this can be very, very small. If the mu n's are, scaling with n, and then this will be exponentially small, and you're never going to get the noise exponentially small with polynomial effort. So, this is a limited method. Yeah, so that we completely agree with. But since it's NISC error, we can try some heuristics, and we can just see how well it does. So that's so the second thing is, how do we get this signal? And now this is something that is actually based on sort of old node of Sergey that I always wanted to use for something, and that we now have kind of found maybe a use for, and we've expanded a bit. And there's still some generalizations, and we're going to write this up in the next few months, hopefully. And the result is this. So I have a stochastic Hamiltonian. I'm not explaining what stochastic is in this talk. Sorry about that. Okay, so stochastic in some basis, and I have some state, an input state, and this is the state of which I want to estimate the spectral content, so to say. And my assumptions on the state for this thing to work is that these coefficients are real. Actually, there may be a relaxation of it, but we just haven't had time to look at it. Secondly, we have to be able to sample from the probability distribution determined by the state efficiently, which is quite constraining in some sense. And given x and y, we have to compute these fractions. Now, this is so you know, if it is a product state, it works well. If it's not a product state, you know, maybe you have to run a Monte Carlo, some heuristic thing to start, you know, sampling from this distribution. Of course, you know, this is a limitation, but you also know that for phase estimation, we also have a limitation because we have to prepare this state on the quantum computer. Now, on the quantum computer, you may have more tools with running a low circuit or do some adiabatic algorithm or so. Okay, but these are the preconditions. And then we define a Monte Carlo algorithm which outputs an estimate for this quantity. So we take the state, then we take the terms in a Hamiltonian, and we kind of trotterize them. Let's say we trotterize them in L steps. So we take a sequence of these guys for L rounds. And here it looks like every term is only used once, but that's not really relevant. We just, because this comes out of some trotterization. But each of them acts on order 1 qubits. And we also make sure that the largest eigenvalue of these Hamiltonians is less than 1. And then, okay, so the claim is we can write down a classical Monte Carlo algorithm which outputs an estimate for this quantity such that, you know, probability that this quantity, that they're close, is less than epsilon, is large. And it runs efficiently. So it runs in steps, you know, polynomial in L or linear in L, you know, efficient in 1 over epsilon and 1 over delta. Of course, if this is exponentially small, the algorithm would often output 0, right? But the way I can give you a bit of intuition way it works is that we write, you know, we put full bases in between here, and we've set up a stochastic process, something where we move to a new configuration depending on these little matrices, and so we set up sort of a walk, and then, you know, depending on this whole path or this whole walk, we estimate a quantity, and that the variance of this quantity is bounded, and the expectation value is also bounded, and so on. Okay. Now I want to just finish up with we've done this. Maarten Stroeks, who was on the previous slide, has started to implement something like that just on a, you know, trial model, transverse field Ising model. So it's stochastic. We work in the paramagnetic regime. We take a state, and the state is actually just the ground state if this transverse field is completely dominant, and a state which is sort of a single particle excited state. So uniform position of these, you can sample from that efficiently. And then he takes a certain number of trotter steps, and the number of sampling points is 4,000 here. And here you see, as a function of tau, you see the decay. And you see there are two, actually it turns out there are 2 frequencies. Well, that's not so surprising. You'd expect 2 frequencies in a signal. And here, so this is the data you get from the Monte Carlo, and this is the data that you get from your quantum phase estimation, which is an oscillatory signal. Actually, there's something I don't fully understand why it's going down here, but that's a different thing. Okay, and there is estimates that we have, so you can look at the exact energies and the estimates you get from the quantum phase estimation or the Monte Carlo method. And these are actually not so good in this example, and this is mostly because the trotter error is still quite high. We could easily, because the circuits here, if you look at, you know, if you have to translate this MS35 in terms of a quantum phase estimation circuit, is maybe 70 deep. So it's not very deep. So we could go a bit further that way. Okay, so let me just conclude. Yeah, okay, so we believe we should do a bit more with this to explore this to see how it works for more interesting models that are stochastic. I think it's important to understand the difference in sensitivity to sampling noise for this matrix pencil method. Then maybe there's an idea of using both, you know, people like this sort of hybrid stuff. So for example, you know, Monte Carlo, you know, that's, well, there's some limitations we have. Can we use both quantum phase estimation and Monte Carlo to kind of, you know, and then you can sum the signals, but then you need to, you know, you need to do this for the same K. So if you say I'm making my Monte Carlo very deep, I can go to a very large capital K, but my quantum phase estimation is very noisy, so I want to only go to very low K. That doesn't really work. In this case, I'm just sort of assuming you have to go to the same K both. We don't know whether this is better than, you know, the estimates you get from QPE or the average of those estimates. And then there's another question about quantum phase estimation and the effect of noise that we have some initial thoughts on in the in this paper by O'Brien, Tarzinski, and Terhal. So I'd like to leave it at this and hope you have some questions.
Great, thanks for the lovely talk, Barbara. So just having a look at the questions now. Perhaps I'll ask a quick question whilst they come in on the Slack channel. So you've used these techniques from Fourier analysis. Do you think there are other techniques from Fourier analysis that haven't yet been applied to studying algorithms like phase estimation that would be fruitful?
Yeah. Okay. So this matrix pencil technique, like this Moitar paper, uses Fourier analysis. But then I've had questions. I know I've looked at phase estimation, which I said where I felt like I couldn't quite analyze it, and maybe this is in. Let me go back to this slide. Like, well, okay, so I don't really know. I've wondered whether there's a use of wavelets or other things. You know, you look Fourier transformed, but there are other transformations, and do we actually, you know, are some versions of phase estimation interpretable as different sort of, you know, wavelet transforms or so on? But this is just, you know, I don't really know. I thought about it and then didn't work. So.
Okay, thanks. Yes, so we have a question from Gianetta May, who asked if you could elaborate a bit further on what analog phase estimation and why you refer to it as analog phase estimation.
Okay, yes, the thing is that I find, okay, so analog phase estimation, I mean more like, okay, so I have built a chip with a natural time dynamics, and maybe I'd like to assess it in terms of what Hamiltonian implements, and you know, if I turn some knob, what Hamiltonian implements. And for that, in order to assess that, I'd like to use phase estimation, or, you know, because this is, but then what you see, for example, in this circuit, is you see that it's, you know, you need an ancilla, you need to do the controlled unitary, which is not so useful. So can you, you know, can you get around this? Can you use these ideas, which are a little bit more, you know, computer sciencey, in terms of, you know, doing, characterizing your chip or doing benchmarking? And then, okay, so that's one thought. And the other thought I had is like, if I look at the circuit and say, well, you know, this qubit is really important, and these are, you know, anything can go here, it's okay. So if I make chips, shouldn't I sort of be trying to, and also this qubit talks to everybody. So shouldn't I be making a chip that is kind of designed to have that connectivity? Because this is, if this is the workhorse of like your simulations, well, it's not only the workhorse, but if this is a very central component, why shouldn't we build, you know, things around it? And that's not, of course, this is hard because this qubit has to talk with everybody. And then if it has to talk with everybody, you can replace it with a cat state, but then it decoheres more readily and so on. Yeah, but I thought maybe we can take some inspiration from these techniques, just doing sort of physics on, you know, chips, to characterize chips and so on, or to build different ones that are more adapt to running this type of algorithm. Because, you know, you're not sensitive to the noise here, you're only sensitive to, you can say, well, what is, in this circuit, what types of sources of noise do I have and how do I affect this outcome? And we started doing that a little bit in this O'Brien et al. Paper. Yeah.
Great. So Joel Klassen has a related question then. So have you seen anything in the literature about tailoring phase estimation to local Hamiltonians? I guess using local controls instead of having one big non-local control as in the standard phase estimation?
No, I think not. But the point is, what I find with phase estimation, that like I said, literature is not very, I mean, it's very hard to find everything. There's so many papers out there, so maybe I probably have missed things. But I also actually, you know, I was preparing the talk, I thought, well, maybe somebody will ask, well, how deep are these circuits with phase estimation compared to variational things? I'm not even sure, maybe somebody can chime in, how well these comparisons have been made. Like, well, we did some small circuits like that on a noisy chip for this paper with O'Brien et al. And the performance was not so good with noise. But yeah, the question is, like, if you use a variational thing to estimate the circuit or this, how much worse is this? If you use the most clever techniques of trotterization? I don't know whether the answer is no.
So I had a question about the n, so the number of coefficients in the initial state.
Yeah.
So you mentioned right at the beginning that this should be small, and it's clear throughout the talk that it needs to be small. So, I mean, is that generally true, or
no,
is that an assumption that you need to make? And
yeah.
could you say
no,
a bit more
I can
about
tell
that?
you what so we did, you know, you can, so let's say n is kind of large, and the way you construct these matrices G0 and G1 is that they'll output fewer eigenvalues than n. Now, what we see, but we haven't done extensive analysis, they just sort of bin things, meaning that if your spectrum looks like there's a bunch of eigenvalues here and a bunch there, then you just get the sort of average of what's over here and the average of what's over there, because you get fewer eigenvalues, but they kind of interpolate, you know, between the real, they give an approximation of the real spectral content. But I don't know that was just some data, so I don't know what bounds there are on this, like how, you know, whether you really get an average and how the AN actually plays a role. AN is this probability, right? Because you think if, like, you know, one eigenvalue has probability 1 minus epsilon, and you know, and the others are very small, then you probably pick up more of that one eigenvalue, right? So yeah.
So I have a question about stochastic MA. So from Alex Grillo. So do you think that this new Monte Carlo algorithm could have consequences for better understanding stoch MA, since it allows to estimate energies of eigenstates with non-zero eigenvalue, in brackets, as far as I understand it?
It's hard to say. Yeah, because the focus, yeah, I don't know. I'm not sure I can answer this. So the focus is that we have an algorithm that's efficient in estimating G of tau, but then you can say, well, okay, what's the use of G of tau? I mean, that's the weakness of it. So the point usually with Monte Carlo is that you do something, it's very hard to prove it's efficient. Now, so here we have something that is, at least you can prove that I get G of tau, but that is maybe in some cases decaying, and so I don't know whether there's a sort of rigorous use of this. I mean, I can tell you where it came from. So actually Sergey wrote this up because there was something like, well, maybe we should have some stochastic polynomial time class. And the idea was that you take you take a state with all zeros as input, so not this state, this phi state, it's an easy state, and then you apply little gates, which are these guys. And these are just sort of non-negative, you know, actually they were non-negative projectors. And then you look at the overlap with the output state, and maybe that was hard to simulate classically. And that turned out to be easy to do. So, so we wanted to say, okay, so you have stochastic MA, but you do have some kind of, you know, something beyond BPP, but which is stochastic. That looks hard to simulate classically. That's where it came from. Okay. Yeah.
Great, thank you. Yeah, so perhaps returning to the earlier part of the talk, so there's a question from Ben Nyhoff. So in the generalized eigenvalue problem, when G0 is non-square, it can still have a right or a left inverse, which would transform it into a standard eigenvalue problem, but might not give you as many lambdas as you wanted. Is that relevant? And maybe he missed something in the slides.
Well, what you do when it's non-square, you compute this pseudo, pseudo inverse of G0. But I'm not sure that that answers his question. You invert G0 on its support.
Yeah, I think that makes sense. Thank you. So another question on this. So usually these Vandermonde matrices. So sorry, this question comes from Changyong Sao. Usually Vandermonde matrices are badly ill-conditioned. So does that create a problem when you compute the coefficients of the AN from the signal?
Yeah. So this is a good question, because actually this work by Moitra and also other people, and also there's work on decaying signal where they have looked at this Vandermonde behavior. The results really rely on bounding this condition number. That's really some of the hard work they have to do, because the matrix. So the thing is that these lab decays are the well, it depends on. So the point is, it depends on where these lambdas are sitting, right? If the lambdas are all okay, so they're complex only, so sigma n is 0. So they're sitting on the unit circle. And if they're well spread around, meaning the gap is large, then this condition number is well behaved, or sufficiently well. But then if they're, you know, if they're on top of each other, then this condition number is not so good. And that's where you get this condition K has to be large. You know, there's some conditions that result in that. And there's also literature I found on the condition number when they're not, they're just somewhere in the unit circle. So not just on the edge, but in the interior. But what I haven't seen is how that, yeah, and so these condition number directly affects how well you can estimate the vector A. If that's your goal, right? You could say, well, maybe I don't care about A, I just want to calculate the eigenvalues. Yeah.
Great, thank you, Barbara. So that's all the questions we have for now. I'm sure there'll be more on the Slack channel afterwards. So let's finish up there. I'd just like to thank you again for a wonderful talk. So we're starting again with session 6 at 11:40. Thanks, everyone.